Oh, it looks like it's time to meet the great nuclear physicist, Mr. Dr. Professor Hamza. I hope I learned something new today.
Who are you?
I'm a reporter, remember? We scheduled an interview today.
Oh yeah, how rude of me. I almost forgot. Please let yourself in. Make yourself at home.
Oh, this is quite the lovely home you have here.
Please have a seat.
So, Mr. Dr. Professor, how did you become the greatest nuclear physicist in the entire world?
Yes. That happened all the way back in 1976.
Fasten your seatbelts.
Doctor, we have a successful fusion reaction.
Power of the sun in the palm of my hand.
Okay, Mr. Dr. Professor Jawad Auto Octavius, I need you to wake up so I can perform your checkup. Mr. Dr. Professor, what's going on? What's this? It should be stable. Hold on. Let me go call the other nurses. Oh, what is it? Mr. Dr. Professor, what is it? Speak to me.
Complete high legacy.
What? No. What is this? Mr. Dr. Professor. Wow, it's amazing how a doctor can become a nuclear physicist so quickly.
Yeah, it's pretty crazy.
Can I see some of your research?
I'll show you the basics. And if you understand it, I'll consider making you my student.
To begin, I'll explain to you what nuclear fusion actually is. Nuclear fusion is a reaction between two or more atoms when the two atoms come close enough that they can merge at the subatomic level. So the subparticles, the protons and the neutrons inside of them, can merge and form an atom of heavier element. The difference in the mass of the reactants and the mass of the products is released as energy. So the first step in order for nuclear fusion to take place is two hydrogen protons collide and one of them changes into a neutron, and the reaction emits an anti-electron and a neutrino. This reaction forms a deuterium, which is a stable isotope of hydrogen. In the second step, a third proton is captured by the deuterium, and this reaction emits one photon, which is released as energy, and it also creates a stable isotope of helium called helium-3. Steps 1 and 2 must occur twice before step 3 can occur. This reaction combines two helium-3 nuclei and yields two protons and a helium nucleus.
Thermonuclear fusion is when matter is heated so much that it turns into plasma. This type of fusion only occurs due to the high kinetic energy of the atoms in this reaction. It causes the atoms to collide so much that a fusion reaction occurs between the either deuterium or deuterium-tritium atoms. This is the only type of fusion that we have created so far that achieves a sufficient net yield of energy. And the only problem with this type of fusion is we have no way to control the energy that is being released.
Now I will be talking about inertial confinement fusion reactors and how they conduct nuclear fusion. So first, laser beams or laser-produced X-rays rapidly heat the surface of the fusion target, forming a surrounding plasma envelope. Then the fuel is compressed by the rocket-like blow-off of the hot surface material. After that, during the final part of the capsule implosion, the fuel core reaches 20 times the density of lead and ignites at 100 million degrees Celsius. The thermonuclear burn spreads rapidly throughout the compressed fuel, yielding many times the input of the energy. Now I will talk about nuclear fusion through magnetic confinement reactors. So with magnetic confinement reactors, you don't have to worry about finding a material that can withstand the high temperatures of nuclear fusion reactions. This is because the current is induced by changing the magnetic fields in the central induction coils, and even though it exceeds 1,000,000 amperes, the magnetic fusion device keeps the hot plasma out of contact with the walls of its container by keeping it moving in a helical or circular pattern. The magnetic force on the charged particles and centripetal force together act on the moving particles to keep it out of contact with the walls.
Inertial electrostatic confinement is when the gravitational field of superconducting magnets are used to heat up ions. This is one of the easier devices to make, and scientists have created some of these devices at home, but the reaction does not yield significant amount of energy compared to the other methods to do any good.
So now I'll be talking about something called a pinch and how they relate to physics and what they are in general. So in the late 1930s, a detailed plan was developed for a pinch device, a device that compresses electrically conducted filaments, also known as plasma, using magnetic forces. So how do pinches actually work in fusion? So in nature, natural phenomena such as lightning bolts, electric discharges, solar flares, etc. demonstrate pinches. But in fusion, they are applied by applying a huge voltage across a tube which is filled with deuterium gas, and if the multiplication of the voltage and the charge is higher than the ionization energy of the gas, then the gas ionizes, which creates a magnetic field perpendicular to the current. This pulls the material together, which fuses the atoms together, which creates fusion. There are many types of pinches, but the type that is best for creating fusion is something called a Z-pinch. The concept of Z-pinches was discovered by George Paget Thomson and Moses Blackman in 1946. The Z-pinch is basically a plasma confinement system that uses electrical currents in the plasma to generate a magnetic field that compresses it. The name is basically referring to the direction of the current of the device, which is the Z-axis.
So, did you get any of that?
Not really.